So you probably barely even remember starting this chapter. What makes things spicy? We started way back when with tasting spicy things, and then we ranked the pan using milk and water, right? Water and milk. And we found out that milk got rid of the spicy taste in our mouth better than the water. Okay? And that's what we started out with. And now here we are at the end, and we're asking ourselves, what did this have to do with everything that we've done in the past month? Okay? The very first thing I had you do was look at this capsaicin molecule, okay? And we said, what's different about this? Now, you'll have to remember what you were coming into this chapter, who you were. You knew that Na lost an electron, Cl gained an electron, and they made what's called an ionic bond. That's about all you knew about bonding. And then all of a sudden, I show you this big fat thing right here, and we notice a lot of things. It's big, it has bonds like single bonds, double bonds, and it's not made up of anything except for nonmetals, okay? So it is not an ionic compound. Ionic compounds are when a positive charge and a negative charge get together. They make this big crystalline solid that keeps adding and moving on. And this instead, this capsaicin, that's called a molecule. And it's a type of bond called a covalent bond. And I also like to call those molecular bonds because then it reminds you that they make molecules. So where did we get this from? If you look on the backs of your periodic tables, you will see there is an electronegativity chart. In Unit 1, we started with ionization energy. That was because we were making ions. But then we quickly transitioned to essentially calling that electronegativity. And that's because we're now dealing with molecules that have covalent bonds between them. It turns out that the trends are exactly the same, so you don't have to worry about it. And the reason for the change in electronegativity is exactly the same as ionization energy. But from here on out, we're going to talk about electronegativity. So what we noticed was when you're talking about a metal like sodium and a nonmetal like chlorine, when the sodium atom becomes a sodium ion, it becomes more stable because it has 8 valence electrons. Well, those nonmetals are going to try to get to 8 as well because that equals stability. But instead of having a giver and a taker, instead of having a metal and a nonmetal, we now just have nonmetals. Okay, so this entire chapter, and we don't even talk about these guys, right? Those are the noble gases. But this entire chapter is focused right here, and then this little guy over here that we don't want to forget about. So ionic compounds are made of a giver, a metal, and a taker, a nonmetal, and covalent compounds have just our takers. So what we did from there is we saw how they bonded. This was our very first time at looking how things bonded. These are called Lewis dot diagrams, and they look at valence electrons, and you look at how they're bonded together. I got you already at this point thinking about honk 1, 2, 3, 4, because the halogens bond once, oxygen twice, nitrogen 3 times, and carbon 4 times. And if you look at the periodic table, you will see that underneath nitrogen is phosphorus, that also bonds 3 times. Underneath oxygen is sulfur, that also bonds 2 times. And the halogens are, they're group 17. All right? We learned about what a molecule was then and what a molecule wasn't. So a molecule is, first of all, a covalently bonded compound. So here's some examples of molecules here, like methane and caffeine and DNA. But a molecule can also be an element that is bonded together with a covalent bond. So this right here, this is oxygen. It is not a compound. It is an element, but it is bonded together with a covalent bond, so we call it a molecule. And that's just, it's kind of just something that I get picky about as far as molecules go. But we learned about this covalent bond and about how they share their electrons in order to get to 8. Okay? From there, we did a very small amount of naming. A very small amount of naming. And you probably found out rather quickly that this naming doesn't get you very far. Because this naming is only for binary covalent compounds. Right? So we learned these prefixes like right here, SEF6 is selenium hexafluoride. Now, I promise you didn't waste your time, even though this is only binary compounds, which are two things bonded together, and you found out very quickly that it's more than two things often bonded together, because these prefixes are worth knowing. Okay, the prefixes that you see here, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca are important to memorize if you're moving on at all in chemistry because they come back in other places. So, couple little things. The word mono, we only use it on the second word. Okay, you guys know that because we don't call this monocarbon dioxide. That would be silly. Okay. That is carbon dioxide, but mono is on the second word. All right. Now from there, you guys had said that when the milk and the capsaicin are in your mouth, they are having some sort of chemical reaction. So right away, I got that out of the way. There was no chemical reactions that happened in this unit. Okay? In fact, we haven't seen many chemical reactions at all this year, except for the ionic compounds reacting together and sodium and water reacting. But this entire unit, we were looking at interactions. Now, why is that a big deal? Because in order to have a reaction, you need to break apart a molecule. We were not breaking apart water molecules. We were not breaking apart sugar molecules. We were keeping them intact, and we were looking how they interact with each other. So when we looked at their interactions, we were looking at dissolving. So we started this idea right away of like dissolves like. And if you'll recall, the very, very first time we looked at this, all we looked at was to see, do they kind of look alike? Do they have anything in common at all? Okay, we didn't know anything about polarity. We didn't know anything. We said, all right, here's water. I notice here that it dissolves in sugar, and sugar has these little bent portions just like the water. And I notice that hexane here has this long black and white thing, and so does this molecule right here, which is a chemical in vegetable oil. So we started to see if the chemicals kind of looked like each other, they were dissolving in each other, okay? So hexane dissolved with water, or hexane dissolved with oil, but oil did not dissolve with water. So that got us thinking, and I specifically went to the easiest two. These are two clear liquids. They're very accessible for me to get. This is water, this is hexane. So I just said, okay, these are very different from each other. They have nothing in common with each other. Let's see the way they act. So we looked at the solubility. Obviously, they don't dissolve together. Salt solubility, that's kind of an interesting one that at the time you probably maybe didn't know what it means, but now when you reflect, you're like, I can see why the positive and negative charges in salt may be attracted to a water molecule, but not a hexane molecule. Then we looked at the interaction with a charged balloon, and we saw that water was pulled towards that charged balloon while hexane wasn't. We looked at surface tension, we looked at evaporation, which are some things that we visited again towards the end of the chapter. Okay, but I made you draw a model. Tell me now, what makes hexane and water different? Well, the only thing that we knew at this point, we knew a lot about charges. So we said there must be something about water that is making it stickier, that's making it stick stick to other water molecules, okay? And the hexane, sure, it's sticking to other hexane molecules. If it wasn't, it wouldn't be a liquid, but it's not as sticky as water is. So we know about electrostatic force, which are these positive and negative charges, and we kind of took off from there. I let you read a comic, The Polar Bears and the Penguins, was all about polarity. If you are still confused about polarity, go back and look at this again, because you've got a whole new perspective now. But the polar bears and the penguins really focused on electronegativity and the pull of electrons. So things that were more electronegative, in this example, chlorine pulled electrons towards them when they were in bonds, and then this one got the electrons pulled away from it, which made the chlorine become a little bit negative and the hydrogen become a little bit positive. And there we learned about the polar bond. We also did a simulation, and in the simulation we took a deeper dive into molecular polarity. See, because bond polarity is really easy. Bond polarity is just this simple equation right here. It's just subtraction, really, okay? If the bond has something that is CH bond or smaller, if you go to the electronegativity table on the back of your periodic table and you say to yourself, C minus H is 0.35, anything less than that is a non-polar bond. Anything more than that becomes a polar bond. And if you go too far, you're going to cross into ionic bonds, where one is actually a giver of electrons and one is a straight up taker of electrons. But this polar covalent bond, it's kind of sharing, but it's not sharing evenly, right? But this bond polarity was pretty easy, but then we got into molecular polarity, a little bit different. We found out that a molecule is polar if you have lone pairs on the central atom. So when you start looking at your happy atoms, like oxygen has these lone pairs always up here, nitrogen has these lone pairs up here, you're going to start seeing that these are going to happen and they're going to start to make things polar. In addition to that, if you only have one bond, if the bond is polar, it's polar. If the bond is nonpolar, it's the exact same thing. The molecule is nonpolar. But then we also saw something else kind of funky happen. If you have polar bonds and no lone pairs, and it's the same thing, it can lead to a nonpolar molecule. Okay, so CCl4 is a nonpolar molecule, but this only counts if they're the same thing. If I were to take one of these Cl's and I were to replace it with an H, this would now be polar, right? Because it wouldn't be evenly pulling on it. It would give us a net dipole. But this only got us so far because these are very small molecules, right? We know that molecules are bigger than that. And let's go back to that water and hexane. Who cares? Why are we even looking at polarity? Well, polarity then led us to these intermolecular attractions. So this was the first time I mentioned intermolecular forces. So they tell us how sticky something is. Okay, so if the molecule is polar, if you have a polar molecule, then you're going to have those dipole-dipole forces, right? And if you have non-polar molecules, you will not have dipole-dipole. We also found out, in the case of hexane that is completely nonpolar, there must be something that's making it stick together. So I started explaining to you dispersion forces. And I told you that dispersion forces exist in all molecules, but the kicker is the bigger the molecule, the bigger the dispersion forces. And if you look at this chart right here, look at dispersion forces. They can be almost as strong as hydrogen bonding, right? Look at this, 20 plus kilojoules per mole. You don't even need to know what that means. Now, hydrogen bonding is a very special type of dipole-dipole. It's like an extreme dipole-dipole where hydrogen is bonded to F, O, or N. So if you see hydrogen bonded to F, O, or N, it's hydrogen bonding and therefore dipole-dipole, and we know everything has dispersion forces. We looked at the simulation because at this point, I wanted you to start building these from scratch. So I wanted to give you the elements, and then I wanted you to tell me what the molecule is, if it's polar or not. If it is polar, then it means it has dispersion forces. Does it have hydrogen bonding? So you had to learn how to put these things together. Now, if you'll recall, this was your second time putting things together. You put them together way back when they were Lewis dot diagrams, right? You already put water together. You said, all right, we've got an O, and the O has, 6 lone pairs, and then it's bonded to an H, and the H is bonded right there. But when you did this, you didn't understand this idea that this water molecule was going to be bent. Now, some of you bent it because you had seen bent before, but it wasn't really until this simulation that we started not only putting things together, but seeing the shapes. I've had a lot of students tell me that they picture the happy atoms when they're on tests because they can actually picture putting these things together with their hands and making things. So that simulation or the happy atoms is a good way to look at that. Okay, so then we learned about these shapes. We gave them names. These names are on the back of your periodic table. They're just kind of mixed up there for you. But we learned linear. This is 180 degrees. We learned trigonal planar. This is a triangle on one plane. It's when we have 3 electron domains, or in this case, they call it electron dense areas. There's the first bent. This is bent at 120. Here's tetrahedral shapes. There's the tetrahedral. That's when it's bonded to 4 different things, or four atoms are bonded to it. And then there's the trigonal pyramidal. There's nitrogen. Nitrogen loves to make this shape. And then here's bent, like water is bent. Okay, so this bent is actually at 109, whereas this is at 120. And that has to do with the way that these spread out. And there was a video that we watched, and like I said, we did a simulation. And I taught you honk 1, 2, 3, 4. And then we did a little bit more with the happy atoms. I gave you a little cheat sheet on the back of the happy atoms to find out if these molecules were polar or not. And I said, well, are there lone pairs on the central atom? Well, yes, there are. Then it's polar. You could answer yourself, no, there's not. Well, are they bonded to the same thing? This is what I showed you before. Then it's nonpolar if they are bonded to the same thing, and polar if they have different things. Okay? And then I said, if all atoms in the molecule are C's and H's, then it's nonpolar. The benefit of being able to run through these is that now you're practicing your shapes, you're practicing your intermolecular forces or intermolecular attractions, and you're figuring out, if you've got dispersion or dipole-dipole or hydrogen bonding. So we did quite a bit of practice on that. And then this led us to the final activity, and it was big. There was a lot going on, okay? We put it all together. We looked at what we call bulk scale properties, right? We looked at the viscosity of something. That's how sticky and syrupy it is. We looked at the evaporation rate. That's directly correlating to the boiling point. If something evaporates quickly, it is going to have a lower boiling point. We looked at states of matter. Remember, we looked at solids, liquids, and gases. We saw that solids are more stuck together than liquids, which are more stuck together than gases. And we looked at surface tension. So we ranked these, and we started looking at some molecules. The problem is when we started looking at these molecules, they weren't those simple, tiny molecules. They were big. They were things more like you're going to see in your everyday life. So you had to have some gray area there, and you had to be willing to kind of think outside the box a little bit, because, and this is what people hate about this, there isn't any like definite perfect answers than this. But what we can say is that these IMAs in general affect these different things, right? So viscosity, evaporation rate, boiling point, I called them all stickiness. And if you can imagine things sticking together and more sticky, that means they have higher intermolecular forces or intermolecular attractions. I use these interchangeable, okay? So, what was the point? Why did we do this? What gets rid of spicy taste in your mouth better? Milk or water? It turned out it was milk. So, what's up with that? Well, this molecule right here, capsaicin, has a lot of non-polar regions to it. Does it have some polar regions? Yes. So can I say that a capsaicin molecule is polar or non-polar? No. I can say it's mostly non-polar, but what I can say is it's more like milk than it is like water. And you can see here how to cool your mouth down. They've got things about acidic foods. They've got things about carbohydrates. There's more to learn about this. There's actually a lot more science in the reason that these spicy foods go away in your mouth. But what we talked about was that fat molecules and fat-like molecules dissolve the capsaicin in your mouth. So when you have a spicy taste in your mouth, if you put water in your mouth, it is not going to get rid of that spicy taste. It will not dissolve the spicy taste. But if you put something fatty in there, like whole milk or sour cream or yogurt or guacamole, all of these things that have fat molecules are going to help to dissolve the capsaicin. All right? And if you think that all of those little molecules that we talked about, really, like, where do those fit in? Why are we even talking about those tiny molecules when the whole unit was about this big giant thing? Here's a picture that I made for you. Look at this big giant thing. It has all those shapes we talked about. Here's a bent shape. Here's the tetrahedral shaped. Here's the pyramidal shaped. Here's trigonal planar shaped. And from there, you can start seeing polar regions, non-polar. Okay? So there is a point to it. I want to go back, way back in the beginning, to this right here, okay? These are some of the chemicals in vegetable oil. And here's water. So we know that water and oil do not mix. They are not alike enough to mix. These have these big, long, non-polar chains, and water is very polar. But something we also know is that oil is very viscous. Oil has a high boiling point, way higher than water. Oil has characteristics of things with very high intermolecular attractions. So it turns out that oil has high IMAs or IMFs. It's sticky. It's a pretty sticky molecule. And it's not because it's polar. It's sticky because it has very, very high dispersion forces. Right? The high dispersion forces lead to those higher IMAs. We looked at hexane versus butane versus methane, right? Methane was a gas. Butane was a liquid that quickly turned to a gas when it got to the pressure of the room. Hexane was a liquid. And then we look at paraffin, and it was at a ton of carbons and hydrogens, and that was a solid. So paraffin is completely nonpolar. It will not dissolve with polar things, but it is going to exhibit things with high intermolecular attractions. All right, so that's pretty much everything that we talked about and what makes things spicy. So what you can do is on Schoology, there is an answer key to the lab that we did on Friday. I highly recommend going through that and asking questions if you don't understand things on there. And there is also kind of a practice little testy thing with some real life examples. When I do the real life examples on the test, those are sometimes the hardest part, so I made you a few that you could practice. There's also a review. I just caution you, the review sheet goes into much more detail than we went into. Okay, it has like ions, it has exceptions. We didn't do ions and exceptions. We kept things pretty even, Steven. If you want to use happy atoms while you're studying any of this stuff, you are welcome to. It'll help you to get honk 1, 2, 3, 4 better into your head and those shapes better. All right, so have fun studying. Happy study.